we have an expression for capacitance, right? This is for spherical capacitor. And we have used one extreme of it. Right? We have used one extreme of it. What was it? We took RB to infinity. Now let's look at another extreme case where RB is very close to RA. Let me just say RA plus delta X. Okay? So your spherical capacitor is like a sphere within of radius RA and another sphere that has very similar radius, something like this. Are you following? Then our expression becomes, so I will just call this one R, just simply R, and this one R plus delta X. Then your expression is C is equal to 4 pi epsilon 0 R times R plus delta X over R plus delta X minus R. Do you see? What do you get? So this delta X is this difference here, and R is this one. Now, this is approximately equal to 4 pi epsilon 0, and then you have R squared over delta X. Let me write it another way. C is equal to epsilon 0, 4 pi R squared over delta X. What does it remind you? It should remind you epsilon 0 A over D. Okay, A is the area of the capacitor. You see, this inner area is 4 pi R squared, right? And D is just this delta X over here. So in the limit of these being very, very close to each other, you can assume them being as parallel plate capacitor. Are you following this? Yes? So we get the same formula. Yes?
We also can integrate the reciprocal of this to get the capacitance for what? I mean, in series.
Yes, very good point. You can do that. Very good point. So let me continue with this. Let's look at cylindrical capacitors. So what do we have here? This is just practice for you. Oops. So I have a cylindrical capacitor. Let me just duplicate this one, put it over here. Yes. Nice pictures. I think I overdid it, and it looks worse. But let me just put also here and here. Now it makes sense, right? So it's like a capacitor made up of inner cylinder and outer cylinder. Again, the question is the same. What is the capacitance of this system? And to find the capacitance of this system, you need to find how much voltage difference is there because of the charge inside. So let's say there is plus Q here, minus Q here. How much is the voltage drop? And what do? First of all, you assume that the length of the capacitor is much, much larger than RA or RB. Why do you have to assume this? I am assuming that L, the length of the capacitor, is much larger than the radius.
Perhaps the symmetry could be broken.
Yes. If L is almost equal to RA, then there is almost no way for me to do this, to solve this system analytically. Right? I can't apply Gauss's law. It becomes a finite system. Are you following? Yes? Good. So, by assuming this, I am assuming that it's something like an almost infinite cylinder. That's why I can assume that all the electric field lines, for all practical purposes, are going out like this, perpendicular to the surface, perpendicular to the inner surface. Right? Now, what do I need? I need VAB. To find VAB, I use the typical formula. VB minus VA is integral, negative integral of E dot dx, right, from A to B. And what is the electric field inside at any distance r?
Sigma. Ne sigması ya? Lambda over 2 pi epsilon 0 r.
E times the area of this cylinder, the lateral area, right? Let me just plot it like this. The lateral area over here has to be equal to Q enclosed over epsilon 0. Right? How much charge is enclosed?
Lambda times L.
Exactly, lambda times L. I will assume it is Q. So E times A. What about A? 2 pi RL. Very good. So E is equal to Q over 2 pi epsilon 0 L times R. And then I can just take the integral here. VB minus VA is equal to negative integral of Q over 2 pi epsilon 0 L R RA to RB. Right? dr. So, I will just switch VA minus VB is equal to Q over 2 pi epsilon 0 L times ln RB over RA. And VAB is that, so this is VAB. So C was Q over VAB, hence C is 2 pi epsilon 0 L over ln RB over RA. Okay? This is the capacitance for a cylinder. Any questions? Any questions at all? No? Yes?
So we derived the capacitance when we calculate by calculating the potential difference, right? But let's say this capacitance is connected to a circuit and it has a battery that provides, constant potential energy. Then the VAB will be constant and the Q will be changing.
Yes.
But the capacitance remains like this.
Yes.
Like this, in this formula.
Yes. Capacitance depends only on geometric effects, ideally, right? And Q just adjusts itself with respect to the potential that we apply. Yes?
At what point the potential is zero? We choose it, right? I'm really confused about choosing the potential
let me then resolve that confusion. Potential is always 0 at infinity, except when there is an infinite charge, infinite line charge, or infinite surface.
So there is no infinite surface, then we can choose infinity as our reference.
Well, there is infinite surface here.
So where did we choose?
We didn't choose any zeros here. We just looked at the potential difference. Did you see that? We
That's
looked at,
where-
yes. So we are looking at VA minus VB.
Okay.
So we don't care where is 0.
It can be anywhere. And
Yes, it can be anywhere. We care only about, so we don't care in this particular case about the reference point, and we never do. Okay, it's always about potential differences.
John,
Yes.
why this potential is the same with uniform line charge potential in a point? I think it's the same. R0 over Rn and R0 we found.
Yes, because it's the same problem. Just like when you have uniform. So the question is why it is the same with the
Because they don't
linear
define
charge, because whenever you preserve the symmetry, you have the same system. So for example, point charge has spherical symmetry. Also, uniform distributed sphere has a spherical symmetry. So outside they behave the same. Similarly, just one line of charge has cylindrical symmetry, and an infinite cylinder has the cylindrical symmetry. They behave the same. Very good point. All right. Any other questions?
The edges of integral is only change about the hole inside the cylinder, or what if there isn't a hole inside the cylinder? It will be 0 in the bottom line. Is it true, or
There is a hole in the cylinder. What do you mean by there is a hole in the cylinder?
wasn't it?
What do you mean by that? So it's two cylindrical shells, if that's your question.
Yes.
These are two cylindrical shells, and are you talking about the hole in here, or are you talking about the hole in between?
Inside.
In here.
Yes, we did this, right?
Yes?
Okay. What if there wasn't just a cylinder, just the edges will be changed, right? When we are calculating the potential.
I think I'm not getting your question. So is this a solid
Yes.
in your case?
Yes.
If it's a solid, you will get the same answer. I mean, there is just solid cylinder, right? But outside there is a cylindrical shell. And in between there is a void. Is that the question?
No.
No?
I can answer it.
Later, if you want. Okay, that's fine. But you can ask now as well. We have time. Later, okay.
Küçük bir şey sorabilir miyim?
Yes.
Bu işlemleri yapabilmemiz için potansiyel farkı olması gerekiyor değil mi? Artı Q ve artı Q olsa mesela yapamayız.
Yes, so the question is, if it was just plus Q here and plus Q here, we wouldn't be able to do all this calculation. The point is that we are the one who are putting plus Q here and minus Q here for the purpose of calculating capacitance from this definition. Okay? But yes, if it's plus Q here and plus Q here, is there still a potential difference? There is still a potential difference, interestingly, right? Isn't there? Do you see? Yes? So it's tricky. But what we do is we put plus Q here, minus Q here. We solve this problem that way. This is when it corresponds to definition of the capacitance. Alrighty. Any other questions? Okay, let me take you back to high school. But before that, let me just very quickly do this thing with this cylinder as well. And my purpose here is more to teach you a bit of mathematics than to teach you. So let me call this one D, and D is very small than R. So if we are looking at this system at this limit, then our geometry is 2 pi epsilon 0 L divided by ln R plus D over R. Are you following this?
John, what kind of E is that?
I just
There are
squeezed.
2 pi's.
Okay. Sorry. Are you happy? Yes? So, yes, what do I have here? 2 pi epsilon 0 L over ln 1 plus D over R. And D over R is much smaller than 1. Do you see where this is going? Yes or no? Do you know what happens when ln 1 plus x for x much smaller than 1? What happens to this? Approximately?
Which is 0.
Yes, but there's just tiny bit of plus x. So what would it be? It turns out it is x. Okay? Just try it in your calculator. Write ln 1.0001, press equals to, and you will get 0.0001. All right. So this means that in that limit, this capacitance is approximately 2 pi epsilon 0 L over D over R, which is 2, let me just rewrite it in a specific way, 2 pi RL over D. Do you see? We get the same formula again, epsilon 0 A over D. This is the area of the cylinder, right? This area is 2 pi RL and epsilon 0 A over D. Are you happy? Yes, you are. So let's now go back to high school and look at capacitors in series. So what happens with the capacitors in series? Well, so here what we are trying to do is we are trying to create an analogy of this one. So this is point A, this is point B, versus the same system but with just one equivalent capacitance. Okay, so we have VAB here, VAB here. We have, let's say, plus Q here, minus Q here. But here we have C1, C2, and we have, let's say, okay, let me just tell you right away that you have to have the same but opposite charge over here. Because do you see this system is detached from the rest of the system, right? So the total charge on this one must remain, where are you? 0, very good. So then this is, whenever this is minus Q, this is plus Q. Whenever this is plus Q, this is minus Q, this is plus Q. So what you should remember is that when the capacitors are in series, they will get the same charge. How about the potential? What is the potential across these 2 points?
What do you call those points?
Okay, let me put point C here. First of all, do you agree that VAB is equal to VAC plus VCB, yes? And I'm going to call VAB V1 and VCB V2. So what is V1?
Q over C1.
Everybody agrees with this? What is V2? Q over C2, very good. And in the equivalent capacitance, VAB is equal to Q over C equivalent, right? Yes? So from this summation, we have Q over C1 plus Q over C2 equals to Q over C equivalent. And that tells you that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 when capacitors are in series. So it's the reverse of the resistors. When you have resistors in parallel, they have this formula. And when you have capacitors in series, you have the same formula. So let me just write down capacitors in series. Good. Let's look at capacitors in parallel if you have no questions. Yes. Minus Q here, and C equivalent is the equivalent capacitance of that system. Are you happy? Plus Q and minus Q. Thank you.
Also,
Yes?
could you show what this would look like in a real life situation? Like, this is schematic.
Yes. Schematic, yes.
And I want you to show how it will look like in a real life example.
Okay. You take a breadboard.
Yo, bana değil, sınıftan.
You take a breadboard. You put a capacitor like this. You measure 1 farad, right? You put another one next to it. Make sure that the legs touch. Then you measure. It's another 1 farad. And what do you measure? 2 1 farads together. What do you measure? 1 over 2 farad. Thank you very much.
Not like that though. I mean, we haven't seen the dielectrics though, right?
We haven't seen dielectrics yet. Very good. Capacitors in parallel. Let me tell you what happens here. In this case, we are making analogy in the following way. We have capacitors sitting like this, another one sitting like this. They are in parallel. C1 here, C2 here. There is VAB, and we are trying to mimic it with a single capacitor which has C equivalent, A and B. Right? So this one has plus Q here, minus Q here. These ones have plus Q1, minus Q1. They can have different charges now. Right?
Can't they before?
What?
Can't they before have the same charge?
No. I said they can have different charges, but before they can't have different charges. Thank you. Are you surprised? Do you need explanation, further explanation maybe?
In the middle part, it is obvious that
Yes,
but
yes.
other sides maybe that we can charge more.
I see. I see. Yeah, probably there could be some complications, but because you can think of even, we were discussing this before if you remember, you could have 3 parallel plates, okay, which could make things complicated. But in this typical non-malicious kind of physics where we don't try to trick you, then it's fine to think this way. Okay? Now, in this particular case, Q1 plus Q2 must be equal to Q, so that the analogy holds, right? In this case, when they are in parallel, the potential differences need to be the same, right? Because the potential difference V1 is equal to the potential difference V2, which is equal to the potential difference VAB. Let me tell you something that always works, okay? Let's say here the potential is VB. You start from that branch and you go anywhere you want. Let's say you go here, okay? Did you see any circuit element on your way? No. Then the potential over there is VB. You can be as sure of it as your own name. Okay? Okay? Similarly, you start from here, you go here, you haven't seen any circuit elements. This is definitely VA. Do you see? So similarly, you could have gone here. Same. This is VB, this is VA. You can use it in many places in the future. This is just a simple application of this, but you can see how easily you can detect that the potential differences are the same, right? For example, over here, you go from A to C, the potential might change, okay, because you have seen a circuit element sitting on top of it, right? Good. So what do we have here? We have V1 equals Q over C1, V2 equals Q over C2, Q2 over C2, Q1 over C1. Right? But V1 is equal to V2, and they are both equal to VAB. Right? And for this one, VAB is equal to Q over C equivalent. So in this case, I can write it down like this. C equivalent is, help me out here, please. Okay, no. I will write like this. Q is equal to C equivalent times VAB, while over here, Q1 is equal to C1 VAB, Q2 is equal to C2 VAB, and Q is equal to Q1 plus Q2, because we are making analogy and it has to work all the way. And that tells you that C equivalent is equal to C1 plus C2. Okay? Would it be interesting for you if I actually brought capacitors to the classroom and we could measure it here with a special device and we could see that this is indeed the case? Interesting? No? I might do it. I might not do it. I think it would be useful. So capacitors in parallel. All right. Okay, let's look at an example, very simple example. So I have 3 microfarads here. I have 11 over here. I have 12 and 6 over here. And this is the point A. And I have another one here, which is 9 microfarads. A typical question that would not appear in the exam, unfortunately, right? So how would you find the equivalent capacitance between A and B, CAB? Where would you start?
I will start from the right side.
Yes, so you do it for this one.
It is 4.
It is 4 because you did 1 over 6 plus 1 over 12 and you inverted it.
Çarp bölü topla.
Çarp bölü topla. Nice. 6 times 12 over 6 plus 12 equals to what? 4. 4 microfarad. 4 over there, so let me write down 4 microfarad here. Then what do?
Now I sum the parallel ones.
You sum the parallel ones. Let's do it. You sum the parallel ones, which are these ones. And what do you get?
18 microfarads.
3 plus 11 plus 4 is 18 microfarads. Very good. Then finally you do
And çarp bölü topla again.
you do çarp bölü topla again, which means divide, multiply by sum, right? The English translation. So 9, are you with me? 9 times 18 over 9 plus 18. If I'm wrong, please correct me. Do you get 6? Very good. And that's the answer. Right? So should we have a break now? Yes? Let's have a break.